Hi everyone, this is Miss Nguyen. Today I'm going to lecture you guys on chemical bonding. This chemical bond lecture corresponds with the 28 through 29 pages of your textbook. And in this lesson we're going to review in-depth electronegativity. I briefly previewed it on the last lecture, but this one we're really going to dive into it. And we'll talk about why that's significant and how it then directly relates to the type of bond your atoms may form, such as ionic bonds, covalent bonds. We'll also review types of covalent bonds, such as polar and nonpolar, as well as at least briefly preview the reason why those bond types are significant in terms of charges. And that's going to play this last piece is going to play a really huge critical role when we get to Unit 2, because Unit 2 we really dive into why those charges that are remnant on the molecule are really critical to life. Okay, so a couple things I like to keep in mind. These are guiding principles that are really huge. I harped on this one on the last lecture, but these two principles really explain a lot of what's going to be going on in terms of our understanding of when bonds form, how bonds form, and the resulting interactions that occur between molecules and atoms. And that's one, all elements ultimately want a full electron shell with no vacancies. And then two, no matter what, your atom or a molecule will want to interact in such a way that if they have charges, they want to neutralize them. Meaning that if there's a plus end of an atom or molecule or ion, it's going to want to hang out or get nearby some kind of negative charge, even if it's a partial or full negative charge. So that's going to really play a big role as we go through our lessons, and I want you to continually think about that in terms of why certain bonds may form and why certain interactions may occur in our Unit 2, okay? So these are two really major principles that we'll keep going back to. So let's do a quick recap of valence electron shells. So valence electron shells are the outermost electron shell of an atom, and just a reminder, the periodic table is arranged in such a way where we can actually use it to predict the number of valence electrons that are on the outer shell. All right, and ultimately, if you know the amount of valence electrons in the outer shell and how close it is to being full, how many vacancies there are, you can eventually make a prediction on how much an atom wants an electron. That principle is called electronegativity. We're going to dive into that in a lot of depth in a little bit. But before we move on, let's just see if we can figure this out. Looking at these two atoms, which of these atoms wants electrons more? Is going to want to attract electrons more, meaning take in electrons more? Is it the oxygen atom or the aluminum atom? And why? Well, looking at this, you can see that on the second shell, the outermost shell, this guy has 6 electrons, and this secondmost shell is out of 8 electrons. So this dude is his valence shell is about 75% complete, and you're 25% away from getting filled. Just needs 2 more electrons. On this other hand, for my aluminum atom, they have 3 electrons on the third shell, out of 8. So that means they're 5/8 away from having a full electron shell. Actually only 37.5% complete, which means they're over 50% away from getting a full electron shell. So in this case, oxygen is just so much closer to being filled that they're that much desperate. In general, the closer you are to getting to where you want to be, the more likely that atom is going to pull in electrons or get rid of electrons wherever they are in terms of their valence electron shell. So the closer they are to empty, they want to desperately get rid of their electrons. The closer they are to filled, the more they desperately want to add electrons. But because electronegativity is about adding electrons, what that actually fundamentally means is my oxygen atom has a way higher desperation for electrons, which means it has a way higher electronegativity number compared to the aluminum atom. All right? So, an atom can get rid of vacancies by participating in a chemical bond with another atom. This can involve gaining, losing, or sharing electrons in order to complete the outer shell. And based on the electronegativities as well as how close my vacant shells or my valence shell is to filling up its vacancies, you can actually figure out whether or not a covalent bond or an ionic bond will form, whether you're going to share or transfer electrons. So, chemical bonds are a result of all those interactions that occur when you transfer or share electrons. So, it is an attractive force that arises between two atoms when their electrons interact, and oftentimes the reason why these chemical bonds formed in the first place had something to do with their valence electrons, either directly because the valence electrons are being shared, or indirectly because the valence electrons transferred stuff and now there's positive and negative charges, and now these molecules or atoms are forced to interact to neutralize charges. Okay? Now, another term that's going to come up is compound. Now, this definition is your textbook definition. I'm not a huge fan of it, honestly. And the reason why is this word molecule. I wouldn't use the word molecule, personally speaking. I would say, instead, that a compound is a group of bonded atoms of more than one element. And the reason why that is because the term molecule is actually, for chemistry teachers, we tend to exclusively reserve the word molecule for molecules that occur due to covalent bonds. Okay? So this is why it's a little bit tricky. So, yeah, it is a molecule a lot of the time, but not always. And I'll explain what a molecule is later on. Okay, so why do chemical bonds form? Well, I explained. Remember that guiding principle. Atoms want to fill their valence electron shells, and if their valence electron shells are full, then any resulting things they have, they also want to neutralize their charges. They want their positives to be hanging out with the minus. So the reason why that is because having a full shell or having your positives interacting with the minus reduces the amount of energy in the atom that it needs to maintain its state. So it's it takes less effort to maintain its self, or its basic structure, its sense of self, essentially, that it's just better. So as a result, your atoms tend to move or interact in such a way that allows them to reduce their energy load by, again, filling their shells or neutralizing that charge. All right, now let's go into electronegativity. So electronegativity is a really key guiding principle because it's a measurement of essentially that empty vacant shell, how many vacancies we have. Not quite, but it's definitely directly linked. The actual definition of electronegativity is a tendency of an atom to attract a shared pair of electrons. The tendency of an atom, if it bonds to another atom, to grab electrons and drag it toward itself. So essentially, it's how much an atom wants a shared electron. Now, you're going to notice this last column has a cross out here because this last column typically doesn't have electronegative numbers because these atoms over here on the last one typically have full valence shells. So they don't need to attract any electrons. So as a result, there's no measurement, no number that we have for them to measure how much they want to drag electrons towards themselves. Okay? Now, a few things. Generally speaking, as you go up and right, the atoms on the up and most right-hand side are more electronegative. The most famous ones are nitrogen, oxygen, and fluorine. And oxygen is the key dude here because a lot of our stuff, especially in biology, involves oxygen. So if you see oxygen, that's a super electronegative atom. Okay? So just keep that in mind. All right. Also, another thing about this is you may not realize this, but the right side of your table is essentially nonmetals, and the left side is metals. So that actually turns out that the side that typically has the higher electronegativity is the nonmetals, and the side with less electronegativity is the nonmetals. Hydrogen's a little weird, but it even though it's only got one valence electron, it acts a lot more like a nonmetal, and that's actually due to the valence electron. So I'll explain why that is and why it's kind of an exception on the periodic table and why I argue it's definitely a nonmetal. Okay? So, just reminding you, metals tend to have lower electronegativities and nonmetals tend to have higher electronegativities. Okay, so when you look at your periodic table, by the way, the electronegative number you're going to see is on the bottom corner of the periodic table that we use in this class, the one that I typically share out. Now you'll notice most of the electronegative numbers for the metals are under 2 except for hydrogen. It's 2.1, so it's kind of on the borderline. But generally speaking, if you're above 2, you're definitely a nonmetal, or on the nonmetal aspect. Stuff that is on the staircase are actually, they're on the borderline of being metal or nonmetal. Sometimes they're called metalloids because they're a little bit of both. But basically the staircase is the dividing line between nonmetal and metal, except for hydrogen, which is a weird dude. Okay? And why is that? Well, it's the conceptual understanding of electronegativities based on the valence shell. If you get it, you'll understand. So it's not a perfect analogy, but it works pretty well in terms of a broad generalization. And it's basically, if you are 50% or more from full, you have a higher En, which means you are more likely to be a nonmetal. Okay? So let's look at lithium, for example. So lithium has an electronegativity of 1, pretty low. Well, why is that? Well, if you look at their shells, it is, for lithium, they have their 2 on the innermost, and then they have 1 on the second level, and the second level is 8, fills 8. So this person, or this, I don't know why I say person, but this atom is actually only 12.5% full. Now let's look at hydrogen over here. Hydrogen has only 1 electron on its innermost shell, but this shell only has a capacity of 2 electrons max, which means it's not 1 out of 8 from full, it's 1 out of 2 from full. So hydrogen is 50% full. Okay? Now let's grab carbon over here. So carbon over here is 6. Okay, this is carbon, and they're 50% away from full. Now let's look at the electronegativity numbers. Lithium is 1 for their electronegativity number. Hydrogen is 2.1, and carbon is 2.5. And if you notice, hydrogen is a lot more similar in terms of its electronegativity to carbon than it is lithium, and it is due to that vacancy of the electronegativities. So 50% or higher means you have a much larger electronegativity number. And in fact, hydrogen and carbon has such similar electronegativity values that if they bond together, they pretty much share electrons equally, meaning they form a nonpolar covalent bond. We'll get into what that means in a little bit. So that's the idea. By the way, just for understanding, I'll draw fluorine real quick. So fluorine over here is 7 out of 8. So they are, I believe, 7.5% away from full, and they have an electronegativity number of 4, which is the highest. So you can kind of see that trend. Now there's other things that influence electronegativity, but this is like the easiest aspect of it to understand. So how does all this on the valence electrons influence what bonds are formed? Well, generally speaking, when you have instances where you have an atom that really doesn't want electrons and another or wants to get rid of it, while the other one really desperately wants to add electrons, then you're going to be forming what's known as an ionic bond. It's a mutually strong attraction that links ions of opposite charge, meaning you have one ion that is positively charged, one ion that is negatively charged, and generally speaking, ions have if they were formed, have full valence electron shells. So as a result, they are now on the second guiding principle in that they want to neutralize their charge. So they're going to create an attractive force between each other to hang out with one another. And the only thing that will break up this attractive force, because the negative and positive want to hang out, is different negative and positive charges to come in. Now, generally speaking, ionic bonds are going to form between metals and nonmetals due to big electronegativity differences. The electronegativity difference is usually above 2 or above. In the 1.7 to 2.0 range, it gets a little bit dicey, it gets a little bit borderline, but generally speaking, if there's a fairly large difference and for sure one's a metal and one's a nonmetal, then you're going to form an ionic bond. Okay? Now, in this case, usually the ions were made in the first place through the valence electron. So even though the ionic bond isn't technically a valence electron thing, the creation of the ions themselves was a result of those valence electron vacancies. Okay? So in this case, these two atoms, for instance, got nearby each other somehow and ended up reacting. And the reason why they ended up reacting is for sodium over here, with its electronegativity number of 0.9 and chlorine with the electronegativity number of 3.5. So they both have a difference of, 2.6. That's one way to track that it's bonds, but I don't really like to do that. I typically just look at the valence electron shell. And if I look over here with sodium over here has 1 out of up to 8 electron shells or electrons on its outer shell. So it's only 12.5% full. So it has two options. It can either gain 7 electrons or lose 1. Well, it's a lot easier for it to lose 1 electron in order to fulfill its outer shell by losing the outermost shell and just having its outermost shell be its second layer. Okay? Chlorine, on the other hand, if you look at it, it's got 7 out of 8 electrons, meaning it's 87.5% full. And in order to get a full valence shell, it can either gain 1 electron or lose 7. It's a lot easier for it to gain 1 electron, so it's going to drag in electrons whenever they're nearby, an electron that's a little bit loose, not held on as tightly. And because this sodium doesn't really want this one, it's not holding on to it as tightly. So as a result, when they get nearby each other, the chlorine slurps up and pulls in that electron, and it gets transferred. So now as a result, my chlorine and my sodium are happy ions with different number of electrons, but they both still have that completed shell with no vacancies in it. So they are where they want to be. But also, unfortunately, though, they now have a charge that they have to deal with. So, one is positive, one is negative. They just transferred electrons. Oh, wait, you're positive, I'm negative. Why don't we hang out to neutralize our charges? And that attractive force that's causing them to be nearby each other is an ionic bond. So they're not directly stuck together, and in fact they could break apart if another negative and positive substance came in, such as water, but they are essentially hanging out now as a result of their charges. Okay? Alright, this is another way to view the ionic bonds. By the way, this number down here is wrong. It should be 18. But it's just showing you the vacancies as resulting from the different particle number. Okay, remember, the proton number didn't really shift. It was that electron number that shifted. So this guy, sodium, lost 1 electron. The chlorine gained 1 electron. Its naming convention is that when chlorine gains electrons, it turns into chloride. You'll learn that in Chem Honors if you take it. By the way, just a reminder, when we're writing the symbol for an ion, we typically write its charge if there is a charge on its right side. So in this case, this has a charge of -1. Usually the number goes in front of the charge. And this one has a charge of +1. But you keep the number if the charge is 2 or more different. However, if it's 1, kind of like, instead of writing, minus x in math, you could write -1x, but people usually go with this one. Same idea. So in the ion itself, instead of writing 1 minus, we'll just go ahead and just write minus if it's a 1 and plus if it's a 1. All right, you only do it if it's 2 or more. Okay, so that's what happens when one clearly doesn't want an electron and one clearly wants more electrons. But what happens when both are almost full? Both atoms want the electron. Well, in this instance, how they're going to fill their valence electron shell is through what's known as covalent bonds. So covalent bonds occur when both elements, both of these atoms, want to pull in electrons and they still want to fulfill their shell. There's no one willing to give up their electrons, so they're going to figure out a way to both get what they want by sharing. Okay? So, I have a TV, but no computer. You have a computer, but no TV. Why don't we switch off who uses each? Okay? So we both get a little bit of what we want, though we aren't permanent owners. So that's a covalent bond. So it's usually between nonmetals because remember, nonmetals are typically elements that are 50% or more completion and thus want to draw in to fill in their valence vacancies. Okay? So in this case, because they're sharing, they're essentially glued together because they can't separate because they have to pass back and forth whatever they're sharing. So they're stuck together. So as a result, the bonds they end up forming typically end up stronger and more permanent compared to ionic bonds, which are only hanging out with each other due to the charges, and they could be busted up if there was another charged substance nearby. But that is not the case for covalence bonds. They're stuck together because their orbits, their electron orbits, their electron shells are kind of overlapping and hanging on to each other. So what does that mean? Let me draw it out. So in this case, this is an example of a molecule, and you can see here, oxygen typically has 6 valence electrons, and it does have 6 here, but it's sharing 2 of them with carbon. And carbon over here has 4 valence electrons, but it's sharing its valence electrons with other atoms. And if you track it carefully, it's a little hard because I was drawing a little awkwardly, but if you track it correctly, you can actually count them. If you count every single circle that is touching oxygen's outer electron shell, it has 8 electrons on it. If you count every single electron that is touching the carbon atom's outer electron shell, it has 8. Ditto with its oxygen. So they have both achieved what they wanted. All right, so how do these form? Well, I'm going to draw kind of a simple model using oxygen. So a really common molecule is oxygen 2. It's 2 oxygen atoms hanging out with each other. This is the oxygen you breathe when someone says, oh, you're breathing in oxygen. So the way it works, we have our 2 oxygen atoms here, and they need 8 electrons. All right, so what I'm going to do is have them overlap and then share their lone pairs with one another. And if they can share it in such a way that allows them to each have 8, they're going to do it. So now they both have 8 electrons touching their outermost shell. 1, 2, 3, 4, 5, 6, 7, 8 to the guy on the right, and the same will be seen on the atom on the left. Okay? Now, these oxygen atoms are what we call, in their bond, they are actually forming what's known as a nonpolar covalent bond. The reason why is they're both the same element, so they both have the same desire for electrons. Meaning this one has an electronegativity number of 3.5, this one has electronegativity number of 3.5, so there's an equal share or an equal draw on the electrons that they're sharing. Okay? So, as a result, there's going to be no charged ends. Sometimes the electrons that are sharing is being moved around from this guy, or it's being shared to the guy on the left. Now remember, electrons are particles that can't be broken up. Just like if I'm sharing a laptop with you, when we're sharing it, we don't crack the laptop in half. Sometimes I have the full laptop, sometimes you have the full laptop. So sometimes these electrons are moving in this atom, sometimes these electrons are moving around this atom. It's going to go back and forth. But if they go back and forth in equal amount, overall, the charge distribution will be equal around both of them, and there's not going to be an unfair share, and there are going to be no weird charges that are happening. However, there are going to be weird charges when it's uneven. So let's say you need to share your laptop with your little brother and sister, but your little brother and sister is like 3. They don't need the laptop all that much. So you're going to use it 8 hours of the day, and they may use it for like half an hour to watch a YouTube video. You still win. You still have those electrons most of the time, that laptop most of the time, so you have a higher draw on the substances. So if I'm looking for a laptop, I'm going to go to you, not your 3-year-old brother and sister, to figure out who has it or where it is. Now let's look at hydrogen and chlorine. In this case, chlorine was almost 87.5 away from being full, and hydrogen without chlorine's help was 50% away from being full. Remember, it's 50% because hydrogen has a maximum of 2 on its outermost electron shell. So in this case here, clearly chlorine is closer to being full, and it's more desperate to get the electron, so it has a higher electronegativity. So when these electrons are supposed to be shared, the electrons they're sharing, it's going to hang out and swirl around the chlorine far more often than it will swivel around the hydrogen and be on the hydrogen atom. So as a result, this is going to mean the electrons these shared electrons are going to spend more of their time on the chlorine than the hydrogen, and as a result, the chlorine side is going to be slightly charged. That is the partial positive and partial negative ends. So as a result, chlorine is not fully negative because the electron from hydrogen isn't permanently with chlorine. It's just most of the time with chlorine. So it is partially negative. So not a full +1, but like a 0.7 plus. But there is no such thing as partial charges. So instead we do the symbol called partial minus. It is partially negative, while hydrogen is more often losing the electrons when it should have it, but it still has electrons occasionally. So it's like partially positive, like 0.7 plus. But again, we don't have partial charges. We don't have partial electrons. So instead, we write this symbol, partial plus. So sometimes people also show it through arrows, and they point the arrow towards the atom that has the stronger draw for the electrons. So instead, we're showing that the chlorine atom is yanking on the electron more often by having the arrow point at the chlorine side, and then we draw this plus. Okay? This is how we demonstrate what's known as polarity, pooling of one side and the other, or poles that have opposite ends, one plus, one minus. Okay? By the way, these are some classic molecule drawing overlaps. All right. So let's go into a little bit more on some special terms, and then we're going to go into that polarity aspect I was talking about earlier. All right, so just a quick term. Molecule is more used when groups of atoms are joined together using covalent bonds. So it doesn't even have to be different elements to be a molecule. So in this case, molecules like that oxygen 2 atom, where there's 2 oxygens bonded together because they're sharing electrons, that would still be a molecule. It's just called an element molecule. While a compound molecule would be something that has a covalent bond allowing them to join up. So for instance, sodium, that's Na+, that's not covalently bonded to chlorine minus, these are compounds, but I wouldn't necessarily call them a molecule. It's just an ionic compound. But this guy over here, this water molecule that has covalent bonds because they are sharing that electron, and they have 2 or more different elements. They have hydrogen and oxygen here. So this is another simplified picture of the water molecule. This would be a compound molecule. So that's the idea. Generally speaking, if you have a covalent bond between 2 things that are different elements, most of the time it's going to be considered a polar bond. Not always, but most of the time. All right? So, and as a result, If it's unequally shared, you're going to get those slight partial charges, and that partial charge is often shown with that symbol. I call it a squiggly D. It's like an S that curves into looking like a sideways D. It also looks like a weird warped music molecule to me. But anyways, that's the idea of those shapes. So, polarity is the state of having charged ends on a molecule due to that uneven electron sharing. So polar molecules don't have full charges, they have those partial charges. And those partial charges are often called dipoles. So di for two, poles, because, poles, like the poles of the earth, there's opposite ends. Okay, so di, two poles, two ends. All right, so generally speaking though, when you're drawing your symbol, you're the one that has more electrons dragging toward it always ends up having a slightly negative charge because electrons are negative. So this oxygen here is yanking electrons towards it, so it's partially negative. The way to draw it out is just draw a weird squiggle and then a plus. So like an S that curves into a D and a plus on the corners that have that slight partial charge. Okay? And then when they interact, when there's two molecules with plus and minus poles, the plus and minus dipoles, they end up linking, not too unlike the ionic bonds in terms of neutralizing the charge. This negative side is going to be looking for a positive charge. This positive side is going to be looking for a negative charge to hang out with. So those charges, both from the ions and these dipoles in the polar molecules, have the capability of interacting with one another to neutralize a charge, right? Because these are still charges, they're just partial charges. So I might need 2 of my hydrogen dipoles or 3 of my hydrogen dipoles to interact with a negative ion, a fully negative ion, or maybe even 10 partial dipoles in order to interact with a full ion, okay? But they can still interact. So this is a classic example. My water molecule, so this is a water molecule. This is a water molecule. But these water molecules can interact with their positive end hanging out and sticking to interacting with the negative side of the water molecule. So that's the idea of interactions that occur as a result of those bonds that are formed, which were a result of those valence electron shell vacancies. So, a general rule of thumb, polarity of molecules are going to interact or going to affect those interactions that occur between different molecules. And generally speaking, if you have a polar molecule, it's going to result in interactions that are charged, and they can mix with water, while nonpolar ones can't mix with water, and they're not going to hang out with other charged stuff because they don't have charged ends. Now, just a heads up, it's going to be a little bit confusing, but sometimes polar bonds can lead to nonpolar molecules if those polar bonds evenly pull the molecule in all directions, and it ends up creating kind of like it ends up, because they're all dragging it in the same direction, they end up evenly spreading out their charges. That's complicated, so let's not even worry about it. Just focus on bonds, but realize it gets more complicated, and that's for you to learn in chemistry, especially chemistry honors, but I think also chemistry teaches it as well, okay? But for now, we're just focused on, all right, charged ends often lead to charged molecules, not always, but often. And charged polar molecules will hang out with charged substances, but not non-charged substances or non-polar substances. All right, so there's also a few different ways you can write out molecules, and I just wanted to bring it up. So the most common way is for water, for instance. Okay, you could draw out the whole electron shell diagram, which is very tedious, but you could do it. But sometimes people go, all right, the scientist I'm talking to or communicating to doesn't need all that information. So sometimes people just write down the number of atoms that are in the molecule. So there's 2 hydrogens, 1 oxygen, H2O. But that doesn't show you the way they're bonded. You don't know if hydrogen is bonded to hydrogen, is bonded to oxygen. Like, how is it bonded? Is it like this? What are you doing? Well, that's the whole point of what's known as structural formulas. So even if you're not drawing out all the electrons, you are showing the relationship that the hydrogens are bonded to a central oxygen. Now, sometimes people do, instead of that, they will actually just draw the 3D picture that kind of is more representative of the molecule itself, because the way the molecule shape ends up being formed is the 2 hydrogens are actually a little bit bent up and a little bit closer together with one another. And as a result, with my oxygen, and my oxygen is a little bit larger, so sometimes people like to draw it like this instead, and just show that my oxygen is in the center and slightly bigger than my hydrogens, because my oxygen has 2 shells, 2 orbits, versus my hydrogen, which only has 1. So these are just different ways to represent a molecule, and you're going to see all of them, especially for water. Do take a moment and make sure you know what a structural formula, though, is. So it's lines between atoms used to represent covalent bonds. So it's used over here. It's a structural formula, but just a heads up. If there's 2 pairs, so 1 pair of electrons that are shared only gets 1 bond, but if you have 4 electrons shared, you're going to have 2 bonds between them. If you actually didn't know this, each bond that is formed is represented of 2 electrons being hung out for each bond. So each line is 2 electrons. So if you write 2 lines, you're showing, hey, there's 4 electrons hanging out with one, being shared back and forth between these 2 atoms. Nitrogen's even more gnarly. Nitrogen gas, which is known as N2, it's actually the majority gas in the air that you're breathing. It's sharing 6 electrons at any given time, or 3 pairs of electrons. So that's what those lines represent. So generally speaking, the more bonds that are between 2 atoms, the stronger their links, the more difficult it is to break those 2 atoms apart. All right, summary. Valence electron shell vacancies directly relate to those electronegativity, and that electronegativity is typically related to how close an element is to completing its shell. And the closer it is, that it typically has a higher electronegativity number. When both atoms have shells that are closer to complete than empty, they are likely to share their electrons to complete their shell, meaning they're going to make a covalent bond. But when one is almost complete and one is almost empty, what's typically going to happen is a transfer of electrons, in this case an ionic bond. Different electronegativities between atoms that interact will often lead to bond types or outcomes that result in charges. So if there is a full transfer, you're going to have ionic, but if they're just different, then but there's no full transfer and it's like a more minor difference in electronegativities, then you're usually going to have partial charges, not full charges, and that is a result going to be resulting in polar bonds. So just a heads up. This is a quick summary of all the bond types. This is just drawn from information from Pyro slides. By the way, if you have a quick question on, what happens to between 1.7 through 1.9 range, or through the 2.0 range, my answer for you is it depends. Basically just consider, hey, is one a metal and one non-metal, or are both non-metals? And that's going to help lead you to figure out, is it an ionic bond or a really, really very polar covalent bond? Okay? So, for example, hydrogen and fluorine have a difference of 1.9, but they're both non-metals because they're both almost full, so they are actually polar covalent. All right? But there are instances of ionic bonds that can be a little bit less than 2 also. So really pay attention to that. Metal, non-metal, and how full the shells are. That's going to be your guiding answer. But the basic idea, though, is with ionic bonds, you're going to have the usually non-metal fully grab and rip off the electron. While with polar covalent, there's going to be sharing, but one is obviously winning. All right, but with nonpolar covalent, they're both sharing equally, and there's like a nice even share, an even relationship between both. And just remember, this is how you kind of represent those partial charges, either with an arrow or with negative positive, though usually you want to write out a little squiggly S to represent a partial charge of plus or minus. All right, this was the vocabulary covered in this lesson: chemical bonds, compound electronegativity, ionic and covalent bonds, nonpolar and polar types of covalent bonds, molecule, and the word polarity versus dipole. Make sure you understand these words, and if you didn't understand it, please go back and review and refer to your textbook as well. And of course, you can always ask your teacher for clarification. All right, good luck and move on to any other work you have. Bye.